Hello, and welcome to this video about the number line. In this video, we will explore how to read number lines, draw and plot points on a number line, and add and subtract with a number line. Let's get started. We will use a number line to represent numbers in counting order. The number to the left is always smaller than the number to its right. To draw a number line, we first start by drawing a straight line, and then we put arrows at the ends. The arrows represent the fact that the number line goes on forever in both directions. When dividing the number line with tick marks, it is important to place the tick marks equally spaced apart. This shows that the distance from any two numbers is the same. For example, the distance from 1 to 2 is the same as the distance from 2 to 3. The most important number on a number line is 0, because every other number is based off of how far away it is from 0. Numbers to the left of 0 are negative, and numbers to the right of 0 are positive. Number lines continue infinitely in either direction, so the number line you see is always only part of the whole number line. Because of this, even though 0 is the most important number, it might not show up on your number line. For example, your number line might look like this if you're trying to plot the grade you got on your test. Number lines can be used to represent a specific number. In the example we just mentioned, we can use the number line to represent a test grade of 94 by putting a dot above the number like this. Plotting a negative number would happen the same way. Simply put a dot over the number you are wanting to represent. The number line here shows the number -5. We can also use a number line to help us add and subtract numbers. Movement to the right is for addition, and movement to the left is for subtraction. To use the number line for adding and subtracting, we start by plotting a point at our first number. Then we move right or left, depending on the operation, the number of spaces matching the second number. Let's practice by adding -7 plus 5. We will start at -7, and since the operation is addition, we will move to the right 5 spaces. As you can see, we land on -2. Therefore, -7 plus 5 equals -2. Now let's try subtracting 9 minus 4. We will start at the number 9 on the number line, and since the operation is subtraction, this time we're going to move to the left. We move left 4 spaces, which lands us on 5. Therefore, 9 minus 4 equals 5.
Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and -32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit, I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator. The number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers in their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean. Hey guys, welcome to this Simometrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say 1/8 instead of 8, or 1/3 instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8. So our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5, improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3 over 8 is a proper fraction, 8 over 3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9 over 9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3 over 4. We also have equivalent fractions. Equivalent fractions are two different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If two fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. You can't really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8. And that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common, such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
Hi, and welcome to this review of fractions and mixed numbers. Before we dive in, let's review the basic parts of a fraction. Remember, a fraction simply represents a part of a whole. It has a numerator and a denominator, which tells us what the part is and what the whole is. Let's look at the fraction 3/4 as an example. We can see that the 3 is our numerator and the 4 is our denominator. So the fraction 3/4 is really saying 3 parts out of 4 parts total. It can also be helpful to visualize 3/4 as simply 1/4 plus 1/4 plus 1/4. It is very important to remember that a denominator of 4 does not represent the value of 4. A denominator of 4 represents the value of 1 that is divided up into 4 equal parts, or fourths. The type of fraction we're working with here represents a value less than 1 whole. 3/4 is not quite 1. If we had 4/4, that would be equivalent to 1. But we only have 3 out of 4 parts. We see and use fractions that are less than 1 all the time in our daily lives, whether it's for things like recipes or keeping track of time. Recipes often call for amounts such as 1/2 teaspoon of salt, and we often keep track of time in terms of quarter hours, like 3:15 for 3:15. Though we observe this type of fraction very frequently in our daily lives, it is not the only type of fraction. Consider the following scenario. You're ordering pizza for a big celebration. There will be lots of hungry guests at this celebration, so you order 3 pizzas. Each pizza is cut into 6 slices. This means that each pizza has 6 equal parts, and as a fraction, 6 would be considered our whole, or our denominator. If your first guest eats 2 slices, we would represent this as the fraction 2/6. 2 parts out of 6 parts total. But what if that first guest was really hungry and grabbed 7 slices? Again, each pizza was cut into 6 equal slices, so 6 remains as our whole, or denominator. But this time our part is 7. In this scenario, our numerator is larger than our denominator, 7/6. Fractions with a numerator larger than their denominator are referred to as improper fractions. Essentially, improper fractions equal a value that is more than 1. 1 whole pizza would be represented by 6/6, or 6/6. 7/6 represents 7/6, which is more than 1 pizza. This could be visualized as 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 equals 7/6. It can also be written in another form called a mixed number. An improper fraction and a mixed number will represent the same amount, but simply be written in a different form. For example, the improper fraction 7/6 could also be written as the mixed number 1 1/6. Mixed numbers and improper fractions share the same amount, but as a mixed number, the parts are collected and consolidated into as many groups of 1 whole as possible. For example, 4/4 would be grouped together as 1. 7/7 would also be grouped together as 1. Any value where the numerator is equivalent to the denominator would be expressed simply as 1. In our pizza example, the guest took 7 slices from a group of pizzas that were sliced into 6ths. We said this could be represented as the improper fraction 7/6, or visualized as 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. As a mixed number, we would group 6 of these 6ths in order to form 6/6, or 1 whole. By grouping 6/6 together, we can see that 1/6 is left over. We would write our mixed number as 1 1/6. Let's try a few more examples. Let's write the following improper fractions as mixed numbers. 4/3 can be visualized as 1/3 plus 1/3 plus 1/3 plus 1/3. We know that 3/3 is equal to 1, so let's group 3 of these thirds together. We are now left with 1 1/3 as our mixed number. 3 halves can be visualized as 1/2 plus 1/2 plus 1/2. We then know that 2 halves, 2 over 2, makes 1 whole, and we're left with 1/2 left over. So 3 halves as a mixed number is 1 1/2. Let's try one more example, 7/4. 7/4 is the same as 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4. Now we know that 4/4 are grouped as 1 whole. So these 4/4 pulled over to equal 1, and we're left with 1, 2, 3/4. 7/4 written as a mixed number is 1 3/4. This process will take place in reverse in order to convert between a mixed number to an improper fraction. For example, if we started with a mixed number 1 3/4 and we wanted to convert it to an equivalent improper fraction, we would take a look at the whole number. In this case, it is 1. This whole number is really representing the denominator that's in the fraction. In this case, it's 4, so the 1 is equal to 4 over 4. When we combine these 4/4 with the 3/4, we end up with 7/4 total, or 7 over 4. That's all there is to it.
Hi, and welcome to this video covering the least common multiple and the greatest common factor. As you know, there are times when we have to algebraically adjust how a number or an equation appears in order to proceed with our math work. We can use the greatest common factor and the least common multiple to do this. The greatest common factor is the largest number that is a factor of 2 or more numbers, and the least common multiple is the smallest number that is a multiple of 2 or more numbers. To see how these concepts are useful, let's look at adding fractions. Before we can add fractions, we have to make sure the denominators are the same by creating an equivalent fraction. In this example, the least common multiple of 3 and 6 must be determined. In other words, what is the smallest number that both 3 and 6 can divide into evenly? With a little thought, we realize that 6 is the least common multiple, because 6 divided by 3 is 2, and 6 divided by 6 is 1. The fraction, 2 over 3, is then adjusted to the equivalent fraction, 4 over 6, by multiplying both the numerator and denominator by 2. Now the two fractions with common denominators can be added for a final value of 5 over 6. In the context of adding or subtracting fractions, the least common multiple is referred to as the least common denominator. In general, you need to determine a number larger than or equal to 2 or more numbers to find their least common multiple. It's important to note that there is more than one way to determine the least common multiple. One way is to simply list all the multiples of the values in question and select the smallest shared value, as seen here. This illustrates that the least common multiple of 8, 4, and 6 is 24. Because it is the smallest number that 8, 4, and 6 can all divide into evenly. Another common method involves the prime factorization of each value. Remember, a prime number is only divisible by 1 in itself. Once the prime factors are determined, list the shared factors once, and then multiply them by the other remaining prime factors. The result is the least common multiple. The least common multiple can also be found by common or repeated division. This method is sometimes considered faster and more efficient than listing multiples and finding prime factors. Here's an example of finding the least common multiple of 3, 6, and 9 using this method. Divide the numbers by the factors of any of the 3 numbers. 6 has a factor of 2, so let's use 2. 9 and 3 cannot be divided by 2, so we'll just rewrite 9 and 3 here. Repeat this process until all of the numbers are reduced to 1. Then, multiply all of the factors together to get the least common multiple. Now that methods for finding least common multiples have been introduced, we'll need to change our mindset to finding the greatest common factor of 2 or more numbers. We will be identifying a value smaller than or equal to the numbers being considered. In other words, ask yourself, what is the largest value that divides both of these numbers? Understanding this concept is essential for dividing and factoring polynomials. Prime factorization can also be used to determine the greatest common factor. However, rather than multiplying all the prime factors like we did for the least common multiple, we'll multiply only the prime factors that the numbers share. The resulting product is the greatest common factor. Let's wrap up with a couple of true or false review questions. Number 1. The least common multiple of 45 and 60 is 15. The answer is false. The greatest common factor of 45 and 60 is 15, but the least common multiple is 180. Number 2. The least common multiple is a number greater than or equal to the numbers being considered. The answer is true. The least common multiple is greater than or equal to the numbers being considered, while the greatest common factor is equal to or less than the numbers being considered.
Hello, and welcome to this video about computation with percentages. Today we'll learn how to solve different types of problems involving percentages and how this skill can help you in the real world. Before we get started, let's review a few things. First, a ratio is a comparison of 2 or more numbers. Some ratios are part-to-whole ratios, comparing a part of something to the whole group. A percent is a part-to-whole ratio that's expressed as a fraction of 100. For example, the percentage 80% means 80 out of 100. In this case, 80 is the part and 100 is the whole. Solving problems with percentages involves translating a word problem into a mathematical equation. There are 3 types of problems with percentages. 1. Finding the part. 2. Finding the whole. And 3. Finding the percent. We'll discuss these 3 problem types together and work on some examples to help you understand how to solve them. Let's start with the first problem type, finding the part. The first problem type involves finding part of a given number that's equal to a given percent. Consider the following percentage problem. What is 60% of 5? To answer this question, we need to understand the information we are given in the problem. Let's look at each part of the word problem and translate it into an algebraic equation. The first part of the sentence, what is, means what number is equal to. Since we don't know the number in question, we use the variable n to represent this portion of the equation. The next portion of the question is 60%. Since 60% equals 0.60, write 0.60 in the equation after the equal sign. The next part of the question is of. When translating written equations into numerical equations, the word of indicates multiplication. Therefore, write a multiplication sign after 0.60 in the equation. The last portion of the question is 5. Write 5 after the multiplication sign in the equation. From here, solve the equation for n. 0.60 times 5 equals 3, so n equals 3. Therefore, 60% of 5 is 3. Now it's your turn. Consider the following percentage problem. 40% of 20 is what number? Pause the video here, convert the written equation into an algebraic equation, and solve. Now that you've tried this one on your own, let's take a look at it together. The algebraic equation that represents this question is 0.40 times 20 equals n. From here, solve the equation for n. 0.40 times 20 equals 8, so n equals 8. Therefore, 40% of 20 is 8. Great job! The next percentage problem type is finding the whole. In these problems, we are given the percent and its equivalent part. We need to identify the whole. Consider the following percentage problem. 3 is 60% of what number? To answer this question, we need to understand the information we are given in the problem. Let's look at each part of the word problem and translate it into an algebraic equation. The question starts with 3 is, which means 3 is equal to. Start the equation with 3 and an equal sign. The next part of the question is 60%. Since 60% equals 0.60, write 0.60 in the equation after the equal sign. The next word in the question is of. When translating written equations to algebraic equations, the word of indicates multiplication. Therefore, write a multiplication sign after 0.60 in the equation. The next part of the question is what number. Since we don't know what number is being referred to, use the variable n to represent this number. When multiplying a number by a variable, remember that no multiplication sign is needed. We can write the equation with the coefficient 0.60 next to the variable n. From here, solve the equation for n. To solve for n, isolate the variable by doing inverse operations. The opposite of multiplying by 0.60 is dividing by 0.60. So divide both sides of the equation by 0.60. 3 divided by 0.60 equals 5, so write 5 on the left side of the equation. And 0.60 divided by 0.60 equals 1, so write 1n, or just n, on the right side of the equation. Therefore, 3 is 60% of 5. Now it's your turn. Consider the following percentage problem. 50 is 20% of what number? Pause the video here, translate the written equation into an algebraic equation, and solve. Now that you've tried this one on your own, let's take a look at it together. The algebraic equation that represents this question is 50 equals 0.20n. From here, solve the equation for n. To solve for n, isolate the variable by doing inverse operations. The opposite of multiplying by 0.20 is dividing by 0.20. So divide both sides of the equation by 0.20. 50 divided by 0.20 equals 250. So write 250 on the left side of the equation. Then if we divide the right side of the equation, we'll get 1. So we're left with 1n on the right side of the equation. Since 1n is the same thing as n, 250 is equal to n. So 50 is 20% of 250. Nice work! The last percentage problem type involves finding the percent. In these scenarios, we're given the part and the whole, and we need to find the percent. Consider the following percentage problem. What percent of 5 is 3? To answer the question, we need to understand the information we are given in the problem. Let's look at each part of the word problem and translate it into an algebraic equation. The question starts with what percent? Since we don't know the percent, we'll use the variable p to represent this number. The next word in the question is of. Remember, when translating written equations into algebraic equations, the word of indicates multiplication. Therefore, write a multiplication sign after p in the equation. The next part of the question is the number 5. Write 5 in the equation after the multiplication sign. The next part of the question is the word is. When translating written equations into algebraic equations, the word is means is equal to. Therefore, write an equal sign after the 5 in the equation. The next part of the equation is the number 3. Write 3 in the equation after the equal sign. When multiplying a number by a variable, remember that no multiplication sign is needed. We can write the equation with the coefficient 5 next to the variable p, like this. From here, solve the equation for p. To solve for p, isolate the variable by doing inverse operations. The opposite of multiplying by 5 is dividing by 5. So divide both sides of the equation by 5. 5 divided by 5 equals 1, so write 1p or just p on the left side of the equation. 3 divided by 5 equals 0.60, so p is equal to 0.60. Now that we know that p is equal to 0.60, we need to convert the decimal into a percentage to answer the original question. 0.60 is equal to 60 over 100, or 60%. Therefore, 3 is 60% of 5. Now it's your turn. Consider the following percentage problem. 11 is what percent of 20? Pause the video here, convert the written equation into an algebraic equation, and solve. Now that you've tried this one on your own, let's take a look at it together. The algebraic equation that represents this question is 11 equals 20p. From here, solve the equation for p. To solve for p, isolate the variable by doing inverse operations. Simply divide both sides of the equation by 20. 20 divided by 20 equals 1, so write p on the right side of the equation. And 11 divided by 20 equals 0.55, so p is equal to 0.55. Now that we know that p is equal to 0.55, we need to convert this decimal into a percentage to answer our original question. 0.55 is equal to 55 over 100, or 55%. Therefore, 11 is 55% of 20. Great work! Computations with percentages are used all the time in the real world. For instance, store discounts, interest rates, and test scores are often expressed as percentages. Percentages are also used when calculating the tip on a bill at a restaurant. I have one more problem for you to try. This one's a little bit more challenging, but I know you can handle it. Consider the following percentage problem. Rachel is taking her friend out to dinner. When she gets the check, the total is $56.75, not including the tip. Rachel wants to leave a 20% tip. How much money should Rachel leave for a tip? Pause the video here, translate the written equation into an algebraic equation, and then solve. Now that you've tried this one on your own, let's take a look at it together. To answer this question, we need to figure out what number is equal to 20% of $56.75. The algebraic equation that represents this question is n equals 0.20 times 56.75. From here, solve the equation for n. 0.20 times 56.75 is equal to 11.35. So n equals 11.35. Therefore, for a 20% tip, Rachel should leave $11.35. Great job!
Hi, welcome to this video on rational and irrational numbers. Rational and irrational numbers comprise the real number system. This Venn diagram shows a visual representation of how real numbers are classified. The natural numbers comprise the smallest subset, which is also known as the set of counting numbers. These are all positive, non-decimal values, starting at 1. Whole numbers are the natural numbers plus the value of 0. The integer set of numbers includes whole numbers and all negative, non-decimal values. Rational numbers include all the sets seen here, in addition to the fractional values in between. An easy way to remember this is that the word ratio is in the name of this classification. All numbers included in the rational number set can be written as a ratio of integers. If a and b are integers, rational numbers can be written as a over b, as long as b does not equal 0. Clearly, the set of integers can be written as ratios because any integer divided by 1 results in the original integer. As illustrated here, integers can be expressed as fractions in infinite numbers of ways. The integer 3 can be represented as the fractions 3 over 1, 6 over 2, and even negative 24 over negative 8. The integer negative 5 can be represented as the following fractions. And the integer 0 can be represented as the fractions As a side note, these are not the only fractions that result in these integers. They're just a few of the many examples that exist. Fractions can also be written as decimals. For example, 0.1 is equivalent to 1 over 10 because the 1 is in the 10th decimal place. 0.13 is equivalent to 13/100ths because the 3 is in the 100th decimal place and the 1 is in the 10th decimal place. .237 is equivalent to 237 over 1,000 because the 7 is in the thousandth decimal place, and so on. These decimals can be written as fractions, so they are considered rational. Other decimals have repeating patterns. These are also considered rational because they can be expressed as a fraction based on the following proof. The repeating decimal 2.17 represents the digits 2.17171717, and so on. So let's try this as a practice problem. Let x equal 2.17 repeating. The repeating decimal is 2 digits long, which represents the hundredths place. So let's multiply both sides of the equation by 100. 100 times x, 2.17 repeating times 100. This results in 100x which is equal to 217.17 repeating. We moved the decimal over 2 spots because we multiplied by 100. Now let's subtract the original equation from this one, meaning minus x and minus 2.17 repeating. So we have 99x is equal to 215. Notice that the repeating portion of the decimal is now eliminated. Solving for x results in dividing both sides by 99. X is equal to 215 over 99. This is a fractional representation of x equal to 2.17 repeating. This proof shows that repeating decimals are also considered rational because they can be written as a fraction of integers. If you plug this into your calculator, you will get something close to, probably rounded, 2.17 repeating. It is important to note that not all decimals are repeating. Some decimals have an infinite number of non-repeating digits and therefore cannot be expressed as a fraction of integers. These types of real numbers are classified as irrational. While there are an infinite number of irrational numbers in the real number system, most commonly used in mathematics are the square roots of non-perfect squares, like square root of 2, for example, and the constants pi and e. The notation for irrational numbers allows for efficiency in math applications. For geometry, you may recall that pi is equal to about 3.14159 for infinity. This is derived from the circumference of any circle and its diameter. Because the decimal value is non-repeating and infinite, we use an approximate value in math applications. Business applications regarding continuously compounded interest employ the irrational value of e, which has an approximate value of 2.718, again, for infinity.
To get started, let's quickly review what perimeter and area measure. Imagine we have a triangular-shaped yard. If we wanted to build a fence around our yard, we'd need to know the distance around the yard. This is the perimeter. If we wanted to buy sod for our yard so that we could have a lovely green space, we'd need to know the area of the yard so that we could buy the correct amount. And while it might be a bit unusual to have a yard that is the shape of a triangle, you might have part of a yard that you want to fence or sod shaped like a triangle. Okay, now that we know what perimeter and area are, let's figure out how to find the perimeter. We don't need any fancy formula or anything. All we need to do is add the length of the sides together. So if we know all the sides of our yard, we can easily find the perimeter. "20 meters plus 20 meters plus 12 meters gives you 52 meters of fence." Not much to that one. Notice that the answer is given in meters. That's because perimeter is a distance. Walking around the yard would mean walking 52 meters. That's all there is to it. No matter what type of triangle you have, just add up the length of the sides and you have your perimeter. Now let's deal with area. There is an actual formula for finding the area of a triangle. The formula is area equals 1/2 base times height. Let's quickly explain where that 1/2 comes from. The formula for the area of a parallelogram is area equals base times height. If we compare the two shapes, we can see that a parallelogram can be made by two equal-sized triangles. So we can say that a triangle is half a parallelogram, which is where the 1/2 comes from in the formula. For triangles, the formula for area does work a bit differently depending on the type of triangle. Let's start with the right triangles. We have our formula, but the question we need to answer is which side is B and which side is H. For a right triangle like this one, B and H are the two sides adjacent or next to the right angle. It doesn't matter which is which, so let's say that B equals 6 centimeters and H equals 8 centimeters. Now we can plug them into our formula. It's always a good idea to substitute with parentheses to help keep things organized. We've even left the units in so that we can see what will happen with them. At this point, we only have multiplication left to do. So according to the commutative property of multiplication, we can rearrange before multiplying. Now let's solve this. Area equals 1/2 times 6, which is 3. 3 times 8 gives you 24. And centimeters times centimeters gives you centimeters squared. So we end up with our area as 24 centimeters squared. For area problems, the answer will always be in square units. That's because we're trying to determine how many square centimeters will fit in our triangle. We can see that clearly by looking at an isosceles right triangle that has legs measuring 5 units on some graph paper. How many squares will be inside the triangle? We can count them. First, we'll count the whole squares that fit inside, then we'll add the half squares. There are 10 full squares plus 5 half squares, for a total of 12.5 squares. If we use our formula, we'll find the same thing. Now we've seen the formula work and gained a better understanding of why the units are squared. All we have left to do is find the area of acute and obtuse triangles. Let's start with an acute triangle. Note that the height is always perpendicular to the base. From here, we can find the area. Here we have our area equals 1/2 times the base, which in this case is 12 centimeters, times the height, which is 8 centimeters. So we get 1/2 times 96 from 12 times 8, which gives us 48 centimeters squared. The same thing applies to obtuse triangles, except the height or altitude will often appear outside of the triangle, like this. We can see that the height of the triangle is 6 centimeters, and the side it is perpendicular to is the base, which measures 9 centimeters. We don't need the other two numbers at all, so let's plug in the base and the height. That's all there is to it. Here's one more for you to solve on your own. Try pausing this video and then finding the perimeter and area of this triangle. Think you got it? The perimeter is 34 meters and the area is 49 meters squared.
Hi, and welcome to this video about the volume and surface area of a cube. We see this shape everywhere, most commonly with blocks and dice. And then there's the colorful puzzle known as a Rubik's Cube, which is a cube that appears to be made up of smaller cubes. In math, a cube is a special kind of rectangular prism. In most rectangular prisms, the length, width, and height of the shape can all be different, but in a cube, they're all the same. That is to say that the edges are all the same length. There are two important measures of a cube. The first one is the volume. The volume of a cube or any other 3D object is a measure of how much space it takes up. We measure this in cubic units, such as cubic inches or cubic centimeters. It's easy to picture this with a cube. Just imagine that we have a bunch of little cubes that are 1 centimeter tall, 1 centimeter wide, and 1 centimeter long. Each one of these cubes is 1 cubic centimeter. This is our unit of measure. Now let's build something from these little cubes. Let's build something that looks a lot like a Rubik's Cube. We'll start with the top level. We need to make a 3x3 grid of the cubes. Each cube is 1 centimeter tall and 1 centimeter wide. Once we're done with that layer, we can see that we've used 9 cubes, which makes 9 cubic centimeters. Next, we build the middle level using another 9 cubes. Altogether, 9 and 9 makes 18 cubic centimeters. Finally, we build the bottom level, again using 9 more cubes. Altogether, we've got 27 cubic centimeters. Our finished shape is a cube made up of smaller cubes. How many did we use? 9 on each layer for a total of 27. We used 27 1 centimeter cubes, or cubic centimeters, to make our bigger cube. Fortunately, to find the volume of every cube, we don't need to build one out of smaller cubes. There is a formula we can use instead. The formula for the volume of a cube is V equals A cubed. V is the volume and A is the length of an edge. Remember that all the edges have the same length. If we measure the area of this cube, we find that all the edges are 3 centimeters long. So to find the volume, we can substitute 3 for A in our formula. We raise it to the third power, which is 3 times 3 times 3, which gets us 27 cubic centimeters, which makes sense since we needed to use 27 of the little cubes to build our cube. Remember that it's very important to specify the units when giving our answer. The other main measure of a cube is surface area. It's an area measurement, so it's in 2 dimensions. Imagine we were making a paper case for the cube we built earlier. How much paper would we need in square centimeters? If we look at the cube we built earlier and just look at one side of it, we can see a bunch of these 1 centimeter squares. If we count them, we can see there are 9, in fact. So one side is made of 9 square centimeters. But to find the surface area of the cube, we need the area of all the sides, not just one. Fortunately, since a cube is the same length, width, and height, that means that all the sides have the same area, and there are 6 sides. So we can multiply 6 sides by the area of one side, in this case, 9 centimeters squared, to find a total surface area of. That's how much paper we'd need to make our paper case. You may have seen a map like this. Just like with volume, we have a formula so we don't have to build a cube each time we need to find the surface area. The formula is surface area equals 6a squared. The 6 represents the number of sides of the cube, and the a squared is the area for each side. We can confirm that this works by plugging in our edge length like this, and then evaluating the expression. We need to remember to use the order of operations and apply the exponent before we multiply. If we do so, we see that we correctly figure out the surface area of 54 square centimeters for our cube.
Most of us learned how to draw a circle in math class using a compass. All we needed to know was where to put the center of the circle and the measure of the radius to set on the compass. Then we held the compass steady at the center and rotated the pencil part all the way around to draw our circle. If we drew it on graph paper and looked closely, we could probably find a few specific points on our circle. But what if we don't have a compass, or graph paper, or even the radius of the circle? What if we are only given the center of the circle and one point on the circle? Can we find the other points on the circle? The answer, of course, is yes. And that's what we're going to do today. Let's start by looking at the equation of a circle. X minus h squared plus y minus k squared equals r squared. Wow, that's a lot of variables. The x and the y are pretty standard, but the others might not be familiar. The h and the k together make the center of the circle at the point hk. The r is the radius of the circle. So if we have a circle with a center at the point 2, 3 and a radius of 5, our equation would look like this. X minus 2 squared plus y minus 3 squared equals 25. We simply plug in the values for h and k and then square the radius for the right side of the equation. Be careful when h and k are negative though. For instance, if the radius is 4 and the center of the circle is at -4, -5, and we substitute into our equation, we have to deal with subtracting negatives. X minus -4 squared plus y minus -5 squared equals 4 squared. Those two negative signs in a row cancel, and we end up with x plus 4 squared plus y plus 5 squared equals 16. When the center of the circle is at the point 0, 0, also known as the origin, our equation gets simpler. X minus 0 squared plus y minus 0 squared equals r squared becomes x squared plus y squared equals r squared. Simple, right? But we've got a little bit carried away. Let's get back to our problem. If we're given the center of a circle and one other point, can we find 3 other points on a circle? Let's do an actual problem to see how we should get this done. Find at least 3 other points on a circle that has a point at 2, 6 and its center at negative 2, 3. So our point is going to be at 2, 6. And our center is at negative 2, 3. The first thing we need to do is find the radius of the circle. We can do this by plugging in everything we know into our equation for a circle. Since we know the center is at negative 2, 3, we know that h equals negative 2 and k equals 3. Since we know a point on our circle, we can use x equals 2 and y equals 6. We plug it all in and it looks like this. So the formula for a circle is x minus h squared plus y minus k squared equals r squared. So our x and y comes from our point that we're given, and our center is our h and k. So x is going to be 2 minus h is negative 2 squared plus y is 6 minus 3 squared, and we're not given r, so it equals r squared. We deal with our subtracting and negative problem to get this. 2 minus negative 2 is the same as 2 plus 2. So we just replace that minus a negative with a plus sign, and then everything else stays the same. 6 minus 3 squared equals r squared. Then we evaluate what's in each set of parentheses. 2 plus 2 equals 4. So we have 4 squared plus 6 minus 3 is 3. 3 squared equals r squared. We apply our exponents. 4 squared is 16. 3 squared is 9 equals r squared. And then we're going to add them and solve for r. So 16 plus 9 is 25 equals r squared. We'll square root both sides and get that r is equal to 5. Now what? How can we use this information to find more points on our circle? We're going to use a different kind of compass to do that. Let's get out a piece of graph paper and plot what we know so far. Since we know our radius, we can travel north, south, east, and west from that point exactly 5 units to find more points. Moving along the compass points is easy on our graph paper, and since the radius is the distance from the center of the circle to all points on the circle, we know we'll end up on our circle when we travel 5 units. Look at all those points we found. Going north 5 units, we found negative 2, 8. Going west, we found negative 7, 3. Going south, we found negative 2, and going east, we found 3, 3. 4 points. One more than the problem asked us to find. And we're not done yet. We can find even more points if we want, since the given point isn't one of our 4 compass points. If we look to see how far over and up that point is from the center, we can find more points that are the same L-shaped distance away. Here we can see that 2, 6 is 4 units to the right and 3 units up from the center of the circle. So I can draw L-shapes from the center that move 4 units left or right, and then 3 units up and down to find more points. We found 3 more. On the left or west side, we found negative 6, 6 and negative 6, 0. And below our given point, we found 2, 0. Altogether, we now have 8 points on our circle, including the given one. And if we're willing to do some heavier math, we can find any of the infinite number of points on our circle. Since we're on such a roll, let's try that too. First, we need to establish our domain so we can know what x values we can pick. The leftmost x value on our circle is our west point at negative 7. Our rightmost point is our east point at positive 3. So our domain is x is greater than or equal to negative 7 and less than or equal to positive 3. So we can pick any x value from negative 7 to 3 to find its corresponding y values on the circle. Yes, it's plural because there will be 2. So let's pick x equals negative 4 from our domain. Now all we have to do is plug that into our equation for this circle and solve for y. So we're using the x value negative 4. And remember, our center is at the point negative 2, 3. So now all we're going to do is plug that into our equation for the circle. So remember, that's x minus h squared plus y minus k squared equals r squared. So our x value is -4 minus h is -2 plus y, we don't know what that is, that's what we're trying to solve for, minus k, which is 3 squared. And we forgot to write this, but our r, remember from earlier, is 5. So it's equal to 5 squared. So -4 minus -2, that's the same as saying -4 plus 2. So let's rewrite it that way. -4 plus 2 squared plus y minus 3 squared equals 5 squared. Then we'll simplify this to -2. So -2 squared plus y minus 3 squared equals 5 squared. And now we're going to simplify our exponents. -2 squared is 4. Plus, we'll leave this part alone for right now. We'll come back to that later. Y minus 3 squared equals 5 squared is 25. Now we'll subtract 4 from both sides. This gives us y minus 3 squared equals 21. And we'll take the square root of both sides. That leaves us with y minus 3 is equal to plus or minus root 21. And all we have to do is add 3 to both sides. So our answers are y equals plus or minus root 21 plus 3. So the two values are the square root of 21 plus 3 and the negative square root of 21 plus 3. If we're plotting those points on a graph, we can estimate their value by using a calculator to find that our y values are approximately 7.58 and negative 1.58. So we can graph those too. Now we're up to 10 points on our circle. Can you find any more? Pause this video now and try. The answer for all the integer values of x will appear shortly after unpausing. Here are the other points on the circle with integer x values. I hope this video over finding points on a circle was helpful. Thanks for watching and happy studying.